Okay, welcome back, everyone. All right, so again, repeating in the chat. So I just emailed the class, and I do expect the homework one grade to be finally emailed on Sunday. It's all gone very slowly. But otherwise, we're keeping the schedule. All right. So lessons 11 through 18, we're going to discuss the homework today and on Monday. All right. And then the homework is due on Tuesday, March 23rd, the day after the homework session on Monday. All right. The idea being that I would give you 24 hours to work out the tech and upload, right? And then next Wednesday, I'll start the third part of the class. Again, I expect the homework one grades to be emailed out Sunday this weekend. All right. Okay, so today on Monday on the homework. I want to start with a fun 6-minute video on the most fascinating probability midterm I ever took. So I want to start with a 6-minute video. And then in the meantime, go ahead and organize yourselves. And remember, if you ask me the last questions you're having trouble with today, you might be ready to turn things in tonight if you wish. Although I recommend that you stick around for Monday and check your answers, though, right? But you can get your key questions answered today as well. All right. In the meantime, let's go ahead and look at the video. I have one video, 6 minutes.
Hi, everyone. This is Professor Ronald Howard. He's the father of decision analysis, and he's taught many students from Stanford's business school. This professor gave me the most fascinating test I've ever taken in my life. It was the midterm in his decision analysis course. Now, here's what the midterm basically looked like. It was 20 questions based on the material of the course, and each of the 20 questions had 5 options, A through E. Now, you might be looking at this and you might be going, oh, it looks like a Scantron exam. No, no, no. This was not a Scantron test. Each problem had 5 slots corresponding to the 5 possible options, A through E. You did not just check off the one that you thought was correct. You had to assign a probability distribution to each question. So for example, do you see what I mean by that? For example, if you thought there was a 60% chance that the answer to number 20 was B, you put 0.6 here under B. If you thought that there was a 10% chance the answer was A, you put a 0.1 under A, maybe 10% for C. Maybe 20% for D, and maybe a 0 for E. Now here, I should put a sad face instead, and I'll tell you why. Okay, so this was a strange test. You had to assign a probability distribution for each of the 20 questions. Now, if you left an entire row blank, then the computer would automatically put a uniform distribution. So the computer that graded the test would automatically put 0.2 or 1/5 for each of the 5 options automatically if you turned in a blank row for a question. In fact, there are some students who took the test, they got the exam, they put their name on it, they left the rest of the exam blank, they turned it in to the TA, the teaching assistant, and they actually did better than some students who turned in a paper with some numbers in it. Because it was possible to get negative points on some of these questions. And what was the absolute worst thing you could do? What was the absolute worst thing you could do? The worst thing you could do was to assign a 0 probability to an option that turned out to be correct. Only one of the 5 options was correct for each of these problems, like usual. But you had to assign a probability to it, or the computer assigned like a 0.2 for you. If you put a 0 on what turned out to be the correct option, you automatically got a negative infinity for the raw score for the exam. Now, actually, in the end, the scores were renormalized so that even these people ended up with like a 50% or something. But this was very bad. You don't put a 0 probability on something that turns out to be right. Because when you assign a 0 probability, like I said earlier, that's a very powerful thing to say. If you say that something is correct with probability 0, what are you saying? You're saying that it's impossible that E in this case is correct. Well, if you say it's impossible that E's correct and E turns out to be correct, then that's a very embarrassing thing for you to say. So you deserve a negative infinity as your raw score. Actually, I remember one problem where I assigned a 0.8 on an option I wasn't sure of, but I spent so much time on number 3, for example. I spent so much time on number 3, let's say, that I was frustrated and I just wanted to assign a high probability so that I could get a lot of positive points. I believe I got that question wrong and I ended up losing points. I got negative points on the problem. And that was a lesson to me to not engage in the sunk cost fallacy. Look that up. That means that you shouldn't base your decisions too much on the time or investment you placed in it beforehand. So you shouldn't be focused so much on the sunk cost when making your decisions now or in the future. Some of you might apply this to your current personal relationships. Oh, I spent so long with this person, I got to keep going. You might be engaging in the sunk cost fallacy. There were actually a couple of people who did this. They put a 0 on what turned out to be the correct option. They got negative infinity as the raw score. And Professor Howard just shook his head. He looks like a sarcastic Santa Claus. He just shook his head. He swiveled in his chair and he said, "Some people never learn." Oh, and how is a negative infinity possible as the raw score? Well, what the computer did was it took the probabilities that people assigned to what turned out to be the correct answers. And the grading scale was logarithmic. Do you remember how to graph logarithms? I'll go to desmos.com. Do you know desmos.com? Let's graph y equals the natural log of x. As x approaches 0 from the right, you see what happens? The y coordinate, the function value, approaches negative infinity. That's calculus. So based on that logarithmic grading scale, if you put a 0 on the correct answer, then you got negative infinity as your raw score. This was the most fascinating test I ever took. I did pretty well on it, although I lost some points on this one that I learned about sunk cost fallacy on. But it was a fascinating test. I hope you never have a test where you face the prospect of getting negative infinity, though. Good luck.
Okay. So I just add that in. It was an interesting test. You assign a probability distribution to each problem. Or turn in a blank sheet. They did better than some of the people who did this. All right. Anyway, so that was enough of me. The rest of the day is all yours. And like I said, although I'm sure you want to see the answers on Monday, if you get your major answers answered and your major questions answered today, and you look at the answers we go over on Monday, then you're going to be in really good shape on the homework. So they can have an easy weekend, right? Just kind of wait on the verification of the answers on Monday. All right, so let's start this off. Okay, so again, I tend to go by the chat. All right. And go ahead and start listing things. Okay, what were the problems that you had the most difficulty on that you'd like me to explain? Because remember, based on the lectures and notes, I have the right to ask you to show some work based on the kind of work I showed in lectures and notes. That's the guideline. All right. Okay, so let me try to list some. Okay, I'll use blue as my base color here. Okay, so 0.11 number 3. All right. Okay, give it another minute or so. Anything else? Okay, 18 and 2. Okay, 18.2. Okay, and then the requesters, I'll go ahead and ask you what your favorite color is, and we can just go ahead and use that. I'm doing 0 point because I'm used to that in pre-calculus. These are just lessons. Okay, so requesters, think about your favorite colors. I'll use your favorite colors. All right, 11.3, 18.2, 12.3. All right. Anything else for now? Okay, so let's start. Okay, so let's 13.5. Right. So okay, 17.6. All right. And then remember the other problems I might just skim over, and then I might be going too fast for you. So these are problems where I'll be explaining in detail, not going too fast. The others I might go fast on. 11.3, 18.2, 12.3, 13.5, 17.6. Okay. Give you another 40 seconds as we form the initial list here. 11-4. Okay, anything else? Okay, well, of course you can always add to the list, but let's start with these 6. All right, first one, 11-3. You can pick the base color if you wish. Okay, pick a color if you wish. Pink. All right, let's do a hot pink because light pink doesn't show so hot. Let's do a hot pink. Maybe like that. Yeah, like a hot pink. Yeah, should be good. Hot pink. All right. Yeah. So requester gets to choose the color. Okay, that's fine. All right. So lesson 11-3. Lesson 11, number 3. Okay, and we are recording. If for some reason you want me to stop or pause recording, let me know. But I will be recording this and posting it online. All right, lesson 11, number 3. A standard 6-sided. Okay, so I'll color it here as well. All right, a standard 6-sided die is rolled. What is the probability that the die comes up a 2 or a 6? Okay, so when I think about one die, I like to think of the sample space as this array here. Okay, so I imagine 1, 2, 3, 4, 5, and 6. Okay, that composes the sample space for the die, right? The die can come up one of these 6 faces. I mean, a die has dots on it, but if you have 6 dots, you're a 6, and so forth. All right, standard 6-sided die is rolled. What is the probability that die comes up a 2 or a 6? All right, probability the die comes up a 2 or a 6. Now, we're very fortunate because we're assuming that these are equally likely outcomes, ELOs, equally likely outcomes. The super clever among you might be going, well, wait a minute. If you dig in holes in the die, doesn't it shift the center of gravity? Very clever, but don't worry. We're assuming that the standard die has equally likely outcomes. Don't worry about the center of gravity and all that stuff. All right. Okay, equally likely outcomes. So each of these faces comes up with probability 1/6. Okay, so again, 1/6 probability for each. Okay, over here and all these guys. Okay, 1/6 for each of these probabilities. Okay. Yes, happy St. Patrick's Day. Okay. Okay. Go easy on the celebrations, though. Socially distanced, please. All right. Okay. So we have 6 equally likely outcomes. Of these 6, how many of them are either a 2 or a 6? Well, we have the 2 here. We have the 6 here. 2 possibilities out of 6, 2, 6, which I will accept. Remember, in this class, I don't require you to reduce fractions. I don't think that's an intellectually beneficial exercise in our class. This is, of course, 1/3. So I will accept either 2, 6 or 1/3. Right. These are mutually exclusive. You just add them up. 1 plus 1 is 2. All right. And it better be the answer. I do have my answers here. Yeah, 2, 6, which simplifies to 1/3. All right. Any questions or follow-ups? Questions or follow-ups? Next was 18-2. Requester for 18-2. Go ahead and pick a color if you wish. $18.2. Okay, blue. All right. Okay. $18.2. Okay, and that's binomial stuff. Yeah. Okay, so here's lesson 18 on the binomial distribution, and here's number 2. Oh, blue. All right. Okay, now in the class, I talked about this distribution. That was the Senator Smith problem, right? Should I pull up the? I'm gonna pull up the my notes. Okay, grab my notes here. Let's see, 19. Here we go. All right. So the distribution that I described there, that's where is it? Senator Smith. Where was that? Binomial. Oh yeah, was that way up here? Ah, okay. Oh, it was right here. Duh. Okay. All right. So yeah, here's the distribution for Senator Smith. Okay. Okay. So this is binomial distribution. So notice here we have probabilities. These are all between 0 and 1. They add up to 1, give or take rounding error, right? Okay. So n equals 6, p equals 0.7. That's a success probability per person, per American. Okay. And this is an example of a binomial probability distribution. But now I want you to describe in a similar fashion all these. Now I don't expect you to list out a table like this. You can get Excel to do that, right? And later on, I know I haven't done that yet, but later on in the class, I'll show you how you can use Excel to provide binomial probability distributions. Right now, I just need a description like we did over here, all right? So your answers to A, B, and C will be something like this, except that you'll have different values for N and for P potentially. All right. So for A, okay, for 2A, we answer all the questions on a true-false test with 50 questions. So envision this. We have a test. I'm glad I did that midterm video first, right? Okay, we have a test with 50 questions. All right, think about that. It's a true-false test. Okay, so it's like a Scantron, true-false. Okay, but it's not like a probability distribution like before. You just put in a check mark or fill in the bubble, right? Okay. But you didn't study at all, so you guessed randomly on all questions. Imagine that this is a test in quantum physics. So unless you're a quantum physics major, assume this is a test on quantum physics, something that you know nothing about, except maybe equals mc squared, right? Okay, we guess randomly on all the questions. The random variable, let's say that x, okay, is the number of questions you get correct. The number of questions out of the 50 you get correct, okay? So before I put your test through the Scantron, so I'm assuming that you fill out this test, you randomly guessed. You may as well have flipped coins, right? Like heads for true, tails for false. You may as well flip the coin 50 times and fill this in. You're guessing randomly, all right? X is the number it turns out you're going to get correct after I put your test through the Scantron reader, okay? But right now it's a random variable, right? We don't know how many you've gotten right yet, okay? By the way, if you had to guess, about how many questions would you expect to get right? If you guessed randomly on a true-false test with 50 questions, about how many would you expect to get right just from chance? Because I would say, you're saying, I'd say closer to 25. Yeah, because 25 is half of 50. It turns out the average will be half of 50 or 25. Right. So you expect about 25, although 20 would be perfectly reasonable. I mean, if I ran your Scantron through the machine, it could well come up 20, right? But 25 is the most likely number. Yeah. Okay. Anyway, we'll get to that. So what distribution does X have? Now, I don't know how many questions you got correct, but I do know the distribution, right? I can do something like this with 0 through 50, right? In terms of the number you got correct, right? And then Excel can tell you what the probabilities are. All right. So it is binomial. Okay. Why? And you don't have to write this out, but it's because these are independent. What happens on one question has no impact on another question. You have a fixed probability, as we'll see. You don't shift to ABC all of a sudden, right? It's all true, false. And you have a fixed number of questions. You can't ask for more. No extra credit. You can't ask the teacher for extra credit just for you. All right. So it's a binomial distribution with what two parameters? N equals what? How many independent trials do we have here? You're guessing randomly. How many independent trials do we have here? N equals 50. Or if you want the unit, 50 questions, if you want to put the unit. N equals 50 questions. That's a total number of trials. And for each trial, you're either going to get it right or wrong. If you get it right, you add 1 to X. If you get it wrong, you do not add anything to X. Now, assuming that you're guessing randomly, all right, P is what? What is the, for example, on problem number, how about problem number 2? You guess randomly on problem number 2. You fill something in though. What is the probability you get it right just by sheer chance, sheer luck? What's the probability you get problem number 2 right? Let's say I randomly mark true. What's the probability I got that right? 1/2. I agree. 1/2 or 50%. So P is 1/2 or 0.5. These are equivalent to 50%, but in general, we tend to prefer fractions and decimals more so than percents. All right. And there we go. That is the answer to I don't want to reveal too much, so all right. There we go. That's the answer to A. Binomial, it's a binomial distribution. N equals 50 questions. Some people put a unit, some people don't. P equals 0.5 or 1/2. There's no unit to probability. Probability is a pure raw number. There's never a unit for probability. Some people put a unit on N. Okay, that's the answer to 2A. Okay, so if you get that, that's a great hint for B and C. All right. In fact, I want to do this. I'll give you a moment to try to answer these. B, what distributions would these be? On B, we answer all the questions on a multiple choice test with 30 questions. Each question has 3 possible options, A, B, or C, only one of which is correct. We guess randomly on all questions. And again, the random variable is the number of questions you get correct. What's going to be the distribution for B? What's going to be the distribution for B? Describing it. All right. So on lesson 18, 2B. All right. So X, again, is the number of questions you get correct. The squiggle, the squiggle there, the tilde, means is distributed as. Okay. It means is distributed as. Is distributed as, or has as its distribution. That's what that squiggle or tilde is. All right. What kind of distribution? Well, we have the 30 questions, right? We have independence because you're guessing randomly. We have a fixed number of questions. Okay. You can't have individual students asking for extra credit, right? And we have a fixed value for P, the success probability, because these are all ABC now. All right. These are all ABC now. All right. So this has as its distribution a binomial distribution where N equals what? N equals what?
30.
Right. 30. That's the number of trials or questions this time. Now, again, I didn't require a unit, but you could put a unit there. Sometimes I put the unit for N, sometimes I don't. And then you're correct in chat. Okay. P, which is a question?
What does BIN mean?
Binomial.
Oh, excuse me. Okay.
Yeah, it's a type of distribution, binomial. Okay, it means that that you have these characteristics, right? Where you have these independent trials, right? If you get one question correct, that has no bearing on whether you get another question correct, right? It's not like you're on a roll or anything, right? You're guessing randomly. Uh, N is fixed, right? You don't get additional questions right in the middle, and P is fixed. You don't change from ABC to true false or anything. They're all ABC, and you're correct in chat. If you guess randomly on problem number 1, let's say, if you guess randomly, let's say I guess B, I guessed randomly. What's the probability you get that question correct by chance? It is, you are correct, 1/3. Okay, or 0.3 bar. Okay, you need the bar there though, right? Okay, and that's the answer to B. Okay, so binomial distribution, and by the way, you have to put that in, right? You have to tell me it's a binomial distribution, right? Because there are different types of distributions. Like we have uniform, for example, right? Okay, so here we have a binomial distribution, n equals 30 or 30 questions, p equals 1/3. You don't have to show work, but folks, you really have to understand these binomial distributions because we're going to refer back to them, and they're important. I mean, come on, we're talking about good practical problems, right? We're talking about the number of questions you get right on a test. We're talking about medical applications. These are important distributions. All right, let's go to C now. I just do C right here. All right. Lesson 18, 2C. All right. 2C. Over here. 1% of all adults in Fredonia have cooties. Right. 20 adult Fredonians are randomly selected. The random variable X is the number of selected adult Fredonians who have cooties. So again, in this case, a success might be something you don't want. Maybe cooties gives you a bad rash or something, right? Bear in mind, a success might correspond to something you don't want. Often in coronavirus studies, you're counting deaths, right? Okay, so what is the distribution we're dealing with here? X has as its distribution what type? What's it called? Because remember, we're assuming independence, right? Because we're assuming that there are millions of Fredonians, right? And we're just getting 20 of them. So we assume independence, all right? And we have a fixed number of people in our study, right? And we're assuming this 1% doesn't change right in the middle, so they don't discover a vaccine right in the middle, right? What kind of distribution is it? What's the type? It's called binomial. Yes. N equals what? How many people are in our study?
20.
20, correct? Again, you don't need units, but 20, oh gosh, adult Fredonians. You don't have to put the unit. All right, now P. What is the success probability per trial? What's the probability that for any given adult Fredonian in our sample here, that person has cooties? What's the probability?
0.01.
Correct. Remember, we prefer to write the percent as either a decimal or a fraction. So P should be written as either 0.01 or the fraction 1/100th. Either way. All right. And again, that's a pure number. You never have a unit on probability. All right.
Professor,
Yes, there's the answer. Okay, question?
could you explain why it's 0.01?
Yes. Okay. So again, what's going on here? X counts the number of successes. That's always the case in a binomial experiment. X counts the number of successes. Which here is the number of adult Fredonians. Number of adult Fredonians with cooties. Okay, having cooties is a success. That sounds weird, but having cooties is a success. They're the thing we're counting. All right. So here's the fact I'm giving you. I'm giving you the fact that 1% of all adults in Fredonia have cooties. All right. So the idea is that, I'll go to red. The idea is that we have this big pool of adult Fredonians, right? Here's the pool of adult Fredonians. All right. And from here, we're grabbing a sample of n equals 20 adult Fredonians. In the big pool here, we're saying that 1% of all adult Fredonians have cooties. But the thing is, for each of the individual Fredonians in our sample, right, each of these people has a 1% chance of getting cooties. Now, bear in mind, you might be saying, well, wait a minute. If we're sampling without replacement, don't we have dependence? Yeah, but remember the sampling rule. If you have millions of Fredonians and you're sampling 20, we may as well assume independence, because even if you allowed yourself to call the same person twice, it's so unlikely you're going to do that anyway that we may as well assume independence. Okay, so we allow the independence assumption. All right, but that explains why, for any given person in this study of 20 people, adult Fredonians, there's a 1% chance that person has cooties. I'm assuming that you're assuming that I'm giving you a correct statistic here.
So, wouldn't that be 1% of 20 then?
Oh, okay. So let me go back a bit. Let me go back. Get anyone here. All right. So let's say that you flip a fair coin 100 times. All right. X equals the number of heads you get. It's a random variable. We haven't flipped the coin yet. Okay. However, because we have enough information to give the distribution, right? What would be the distribution? X will have a binomial distribution because we have independence between the coin flips. N is 100, right? We're flipping the coin exactly 100 times. Okay. And P is what? Okay. So on the second flip, on the 50th flip, on the last flip, whichever flip you're talking about, what's the probability that a fair coin comes up heads?
Half.
It is 1/2. Correct. So don't think too globally, right? You might be thinking of it too globally. So imagine that we have, in fact, you can think of it as flipping 100 pennies, right? Imagine that we're flipping 100 pennies. I don't have time to draw Lincoln, but imagine that we're flipping 100 pennies, all right? Penny number 1, penny number 2, penny number 100. Okay. Now, one reason why we have a binomial distribution is that the probability of heads stays constant, all right? These are all pennies. If you use a different coin, you might change P, right? But we have all pennies here, right? And we're assuming that these pennies are perfectly fair. The probability that any given penny comes up heads is 1/2. So don't think of it too globally. Just think for any of these individual pennies, what's the probability it comes up heads? 1/2. Likewise, in the cooties example, if you take any one of these people, right? So here are the 20 people in our study. They're very skinny. Here are the 20 people in our study. Person number 1, person number 2. Fredonians are very skinny. Here's person number 20. So take person number 20, for example. Hey, here's an adult Fredonian. Person number 20 in our study, let's say. Here's an adult Fredonian. What's the probability that that adult Fredonian has cooties? It is assumed to be 1%. I'm assuming that the sample is unbiased, right? 1% or 0.01.
I understand. Got it.
You're welcome. Yes. Again, I'm assuming no bias, right? So you're not looking at just one part of the country. You're not just looking at men or women, right? Right. So when you're calculating P, don't think too globally. Like in the test questions, right? I'll go back to that. Right, like true false, right? A true false test. What's the probability you get question number 2, let's say, right? 1/2 or 0.5. Right. You don't have to think, oh, there are 50 questions. What's going on? You're thinking too big. Just think, take question number 2, for example. What's the probability to get that right? 1/2. All right. So 2, a short but important conceptual problem. Okay, because binomial distributions are important, right? What's the distribution for the number of successes? Questions right, the number of people with cooties or coronavirus. Those are serious questions. All right. Any follow-ups? All right. I believe I answered the why question there, right? Okay. Okay. So unless I'll save these, unless you have a follow-up, I'm going to go to the next one. And I'm marking these so I can basically skip these on Monday. I don't want to waste your time. Okay, so lesson 12, number 3. Okay, requester, give me a color, if you wish. Requester gets to pick the color. Teal. Is that like a turquoise? Turquoise, kind of? I like turquoise. Okay, but I like the color. That's okay. All right, I'll go with, without objection, I'll go with turquoise or teal. Like this thing? This thing? Yeah, I like that color. That's probably my favorite color, actually. All right. My colleagues are going, you're arguing colors? What are you? Okay, let's see. It's lesson 12, number 3. Oh, okay. And I can do all 4. Okay, we can go over all 4, right? So that'll be fine. Yeah. Okay, and then I'll just skip these on Monday. All right. Okay, so lesson 12, number 3. Without objection, I'm going to go ahead and go through A to D. Let's do this. Now, please show some work. So either show me a grid or show me the ordered pairs that got you the answers. Don't give me answer only. Do not give me answer only. Either give me a grid or show me the ordered pairs, or at least say something, right? Give me a good rationale. Convince me. Convince me. Like the usual suspects, convince me. Although that guy got tricked, right? Okay. All right. Okay, here we go. This is lesson 12, number 3, right? Okay. Lesson 12, number 3. All right. A. Okay, so I'll use multiple pages for this one. Yes. In fact, what I'm going to do is, so the video might help. I might want to work on the same board, because the same grid, because I'm gonna. I don't want to redo the grid over and over again. You might want to do a big grid as your first step. Do a big old grid as your first step. Okay. All right. Oh, I'll use, maybe we'll use colors here. All right, so red dye goes 1, 2, 3, 4, 5, 6. All right, and then a pure green dye. That's good. Pure green dye. 1, 2, 3, 4, 5, 6. The idea being that in most of these problems, we want to consider the ordered pairs, and we have a sample space of size 36 ELOs. So in the neutral color black, 36 ELOs, equally likely outcomes. Okay. So for example, this over here, the ordered pair 4, 2, that's a 4 on red, 2 on green, and that's one of 36 ELOs in this grid. Each of them equally likely. All right, so let's do A. What's the probability of getting a total of 3 or 5? So actually, just to clarify things, let's start with some die totals. Let's start to fill this out. 1 plus 1 is 2. That's snake eyes, right? And then how can you get a 3? 2 on red, 1 on green, or 1 on red, 2 on green. Remember, that's one reason why we color or distinguish the dice, because 2, 1 is not the same outcome as 1, 2. It's true that they both lead to a sum of 3, but they lead to different situations, right? And you count the 3 twice here, basically. So ordered pairs, right? 2 ways of getting 3. 2 on red and 1 on green, or 1 on red and 2 on green. But they represent 2 different outcomes. Both, however, lead to a sum of 3. All right, now how do you get a 4? I know I didn't ask for 4, but you get a 4 from 3 and 1, 2 and 2, or 1 and 3. And then how do you get a 5? Tell me, how do you get a 5? Give me some ordered pairs. So some of you will write down ordered pairs. Give me some ordered pairs. 4 and 1. All right. What else?
2 and 3.
2 and 3. That's over here. All right. 3 and 2.
Yep.
And
1 and 4.
1 and 4. All right. So now I have enough information to answer A, because I have 36 ELOs total, right? 6 times 6. I have 36 ELOs total. These are equally likely. Okay, I'm going to circle. I'm going to do these individually, actually. In what? Orange? How about blue? Pure blue. Pure blue. All right. I want the 3s. Basically, this diagonal here, this skew diagonal. And I want the 5s, this skew diagonal. This, and this. Count them up. How many of these entries have I circled? One, two, three, four, five, six, right? So the answer to A, the probability of getting a sum. Oh, I guess just to be cute here. Okay, our base color was teal. Let's go with the base color. All right. The probability of getting a 3 or a 5 is there were 36 equally likely outcomes. Out of those, 6 of these slots, 6 of these ELOs give us a 3 or a 5. Bear in mind, that is equal to 1/6, but I don't require you to reduce fractions. Now, I know that there were other problems before where the answer was 6 over 36 or 1/6. Before, I had a really cute explanation. Sorry, I don't have a cute explanation for this one. It was just coincidentally 1/6. Yeah, it was a famous probability. That's by coincidence. So that's the scheme. That's the scheme, okay? And in fact, I'll give you a minute or so. See if you can get B, C, and D. Fill out the rest of the table. See if you can get B, C, and D. B is the probability of getting doubles or a total of 7. Okay, that you could get cute on. C was the probability of getting a 2 or a 4 on the red die or a 3 on the green die. Now that's a 2-die problem. You need the grid. Okay, you can't just have a one-dimensional array. D, what's the probability of getting doubles or a 3 on the green die? So I would recommend doubles on all these, although in theory, B doesn't require a grid, but otherwise you'd have to explain it. C and D, you pretty much need a grid. I'll give you a minute to think it through. So when my clock reaches 8:54. Actually, you might need another minute. How about 8:55? I want to give you a couple minutes. Yeah, you might want more grids. For B, that's correct. Over the 36, right? 12 over 36. That's right. Yeah, don't forget to put over 36. Remember, your final answer is a probability. Okay, and don't forget to don't forget to say hi. All right, 8:55. Now go ahead and keep working. I mean, don't feel rushed. I don't blame you for taking more time. So feel free to keep working. And remember, this is on video, right? So I'll upload the video. You're not going to miss anything. The student is right. Okay, B, I agree. It's 12 over 36. or 1/3. You don't have to reduce the fractions though. Okay, so here's what I'm going to do. Again, remember, you can watch the video. I'm going to erase these bubbles now. Let's fill out the table. Okay, so I'm going to take up your time, but yeah. Okay, sixes. 1 and 5, 2 and 4, 3 and 3, 4 and 2. Whoops. 5 and 1. All right. Sevens. This is the longest skew diagonal. 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. And actually, that's the last one I need, right? Yeah, that's the last one I need because we're answering B. That's the last one involving totals, right? Okay, so actually I can stop at this point. You don't have to do the rest of the table. You can just do half the table. All right. So 3B, there are several ways that you can do this. Oh, wait a minute, but then you have double. Okay, so okay, well, what am I going to do? Okay, so all right. Let's stick with teal because we don't want too many colors, right? Okay, so probability of, oh, this is B. Probability of getting doubles or a total of 7. Sum, right? Doubles or sum equals 7. All right, brute force. There's 36 equally likely outcomes. All right. Now we have 6 entries for the 7. 1, 2, 3, 4, 5, 6. There are 6 ways to get a sum of 7. All right. Now, how many doubles are there? How many doubles are there? We have 1, 1, 2, 2. Don't worry about the sums here. Worry about the 1, 1, 2, 2, right? This is the main diagonal. 3, 3, 4, 4, 5, 5, and 6, 6. All right. 6 on the skew diagonal, 6 on the main diagonal. The student's right. We have 12 total possible ELOs that correspond to this. Don't forget to divide by 36, though. We want a probability. I'll accept this, but that reduces to 1/3. Okay, I'll accept either. All right. Any questions about that? Questions about that? And again, either show me the grid with the marks or write down the ordered pairs or give me an explanation. And you know what? Now, don't worry if you don't get this, but I'm going to explain how you could do this without the grid in case you're curious, because you might be going, oh my gosh, I have to write all this. No, but you have to be kind of clever in your explanation. Let me explain this. Okay, let's talk more about this one. I'll stick to teal. Yeah, I like that color too. All right, teal. All right, so let me explain this in greater detail. Okay, lesson 12, 3B. All right, I can probably type some of it. All right. What's the probability of getting doubles or a sum or total of 7? Okay, now here's the thing. I claim that these 2 events are me's. Do you remember what me's were? Me's are mutually exclusive events or disjoint events. What characterize those? They can't happen simultaneously or together on the same trial. All right. Now, I claim to you that these are me's. All right. Here's a clever way of looking at it. Can you explain to me why it's impossible to get doubles and a sum of 7 at the same time? I'll give you a hint. If you roll doubles, what kind of a number does the sum have to be? Look on this. Look over here. When you roll doubles, what kind of number does your sum have to be? Ask me what kind of integer. Very good. Even. Is 7 an even number? No. There's no way that you can get doubles and even at the same time. Because look, if you get doubles, here are your possible sums. 2, 4, 6, not 7, 8, 10, or 12, right? So these are mutually exclusive events. They cannot both happen. If you're rolling doubles, your sum is an even number, not 7. Okay. So the probability of doubles plus the probability that the sum is 7. Now, normally we'd have to subtract the probability of both happening, but these are mutually exclusive events. The probability of both happening is a big ol' 0. They can't both happen. All right. What's the probability of doubles? We did this in class. Whatever I roll on the red die, what's the probability the green die matches? In other words, doubles. It's 1/6, right? Whatever die, let's say you roll a 3 on red. What's the probability you get a 3 on green? It's 1/6. That's true for all these values of red. Okay, so whatever you get on the red die, it's possible to get doubles, and you get that when you get the same number on the green die. Now, similarly, the probability that the sum is 7, we discussed this in class. You agree that whatever you get on the red die, it's possible to get something on the green die so that your sum is 7, right? Let's say you want to get a total of 7. Whatever you roll on the red die, you can get something on the green die that'll take you to a sum of 7. And there's only one way to do it. If you roll a 1 on red, I'll do this in pure blue. If you roll a 1 on red, you must get a 6 on green. If you roll a 2 on red, you must roll a 5 on green. If you roll a 3 on red, you must roll a 4 on green, and so forth. All right. So by a similar rationale, okay, whatever you roll on the red die, there is a 1 in 6 chance that you're going to get what you want on the green die. In this case, a sum of 7. But both probabilities are 1/6. 1/6 plus 1/6 is 2/6. I'd accept that. That is 1/3. Okay. So again, either show me the grid with the marks, give me the list of ordered pairs, or give me a rationale like this. Okay. But you have to convince me. That's the idea. Convince me. Do not give me answer only. Okay. I have the right to give you no credit whatsoever if you just give me answer only. Okay. Convince me. Convince me. I'm a student who needs a lot of help in stats class. Convince me step by step or by a good, clear rationale. Don't be paranoid. Remember, you don't have to get 100% on these homeworks, but do well enough. You don't have to be perfect, but do well enough. All right. Any questions about that? I love that problem, right? Lots of great ideas here. The answer is 1/3 for B. Are there any questions until we proceed? And don't worry, we'll have plenty of time for the answers on Monday. Any questions before we proceed? We have the other two, right? And I assume you want them, right? Let's see here. Oh, okay. Now again, I'm grading your homework 1s, and I'll email out the grades on Sunday. That's the plan. I'm going to email out your grades for homework 1 on Sunday. I'll be honest. I was grading the first homework for pre-calc, and that really kicked my butt. That first homework assignment for pre-calc kicked my butt. So I've been delayed, but I will get your. I'm really promising myself and you folks to get those graded emails out for homework 1 on Sunday. All right. So I'm setting a target for myself. All right. So anyway, let's go to 3C. All right. So C now. What's the probability of getting a 2 or a 4 on the red die or a 3 on the green die? I highly recommend a grid. It's hard to do without that grid. Although I don't need the totals anymore, so I'm not going to put the totals. I'll put the yeah, I'll just put the basic grid here, the marginals. All right. Okay, lesson 12, 3C. Right, this was a rich problem all on its own. All right, I'll do the marginals for this grid again. Okay. All right. Red die. Red die. And of course, you don't need color on your homework. 1, 2. It might help though. 1, 2, 3, 4, 5, 6. Whatever works for you. And then the green die, the marginal. 1, 2, 3, 4, 5, 6. All right. I use check marks here. On C. Okay, so we're asking, what's the probability of getting a 2? I'm going to do this. A 2 or 4 on the red die, or a 3 on the green die. All right. So we're going to start summing over 36. Well, I mean, I can put an answer in that form, right? You do not have to reduce fractions. Okay, so, well, have you counted out how many of these 36 ELOs will correspond to either this compound event or this event? In a way, they're both compound events, but how many out of the 36? Okay. You can do check marks or something. 2 or 4 on red or 3 on green, right? 2 or 4 on red or 3 on green. Let's do it. Okay, 2 on red. Check, 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 check. Check, X, whatever. Okay, 4 on red. Check, 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 check. 3 on green. Now that's this column over here. Check. Do I double count this? Do I double count this?
No.
You're not supposed to. No. That's why I'm just counting pure check marks. Skip that because we already did it. Check. I already did that guy. Check, check. Okay, it's a pure count. 6 plus 6 plus, okay, that's 12, right? 6 plus 6 is 12. You can count in different ways. 13, 14, 15, 16. There you go. 16 over 36. That does reduce to 4/9, but again, I don't care about reducing. And you don't have to convert to decimal or percent. In fact, I would tend to prefer fractions, right? Because people tend to round off their decimals when they shouldn't. One good thing about fractions is that people tend not to lose accuracy on their fractions. All right. 16 over 36 or 4/9. It's pretty much brute force, okay? Or list out the ordered pairs. Basically, this grid is probably the easiest way of doing it.
Professor Ken?
Go ahead.
So when you counted 3 on the green,
Mhm.
you skipped two of those. You said you didn't want to double count.
Don't double count, right? Because so here's the idea. How many of these 36 ELOs do I count? You count each of these check marks exactly once. Now it's true that for 2 comma 3 and 4 comma 3, it's true that both of these events are satisfied, but
Uh-huh.
that doesn't matter. I mean, if you're in the game, you're in the game. I don't care if you satisfy just one or both. Okay. You count these check marks. These are not special. The ones I'm circling, they're not special. You just count them once each. It just so happens that they satisfy both the events.
Hmm.
But that's the key lesson. You don't double count. So don't put 18 over 36. That's wrong. You don't double count. Any more questions on this? Any questions? Again, the grid is by far the easiest way. Even the formula would have been pretty hard, right? I mean, because it'd be like, okay, 1/6, 2 on red, okay, 1/6, 4 on red, 1/6, 3 on green, but then it might be kind of hard for you to think of the overlap. Basically, the overlap is 2 comma 3 and 4 comma 3, but that's kind of hard to figure out unless you actually see the grid. By far, I think the grid's the best way of explaining it. Okay. Because it's hard to figure out the intersection based on this description. Okay, any questions on 3C before we go to 3D? And this is okay because this is, I mean, once we get through this, that's a good chunk of the homework, right? I mean, plus I do expect some work here, right? Finally, D, the probability of getting doubles or a 3 on the green die. Again, I would recommend doing the table. Yeah, so figure that out. I'm gonna go ahead and do it with a do a new table here because it's pretty quick for me to do it. All right. All right, so lesson 12, 3D now. We're doing D now. All right, lesson 12, 3D. Okay, so same step as before. Whoops. Same step as usual, right? Whoops, not that crooked. There we go. All right. Okay, so Okay, red die. Red die. And of course, I don't care if you put red here, green here, or vice versa. Okay. 1, 2, 3, 4, 5, 6. Green die. It's like Dr. Seuss, right? Red die, green die. 1, 2, 3, 4, 5, 6. All right. Well, again, the probability of getting doubles or a 3 on green. All right. I'll do the neutral color black here. All right. The probability of doubles, or I'll switch to green here, a 3 on green. All right, equals something over 36. That's a good template for these 2 dice problems, right? Something over 36. All right. Count them up, folks. Out of the 36 ELOs, how many will satisfy either or both of these events? Doubles, 3 on green. How many check marks? Or whatever, happy faces. I should do that, happy faces. You want to do that, happy faces? Whatever, okay. How many? How do I do this? There we go. All right. How many out of 36? Okay, well, doubles, that's 1, 1. 2, 2. 3, 3. 4, 4. Again, this main diagonal, right? 5, 5. 6, 6. So that's our doubles, right? It's 1, 6, right? 6 out of 36. But we have 3 on green. Now. 1, 3. 1, 2, 3. 3, 3. Do not double count. Do not double count this. 4, 3. 5, 3. 6, 3. So again, do not double count. And again, you're in danger of double counting this one. Don't double count it. Okay. So we have 6 plus 5, if you wish, or whatever, 11, right? Because you have 6 on this main diagonal, 7, 8, skip him, because we already did him, 9, 10, 11. 11 over 36, which is simplified. And in fact, now not that you would do this, but you could do a formula in principle. I'll show you how it works. Just for kicks, I'll show you how it works. So what's the probability of doubles or a 3 on green? Is the probability of doubles plus the probability of a 3 on green minus the probability of both. Here's another way you could do it. Now, although I wouldn't expect you to do it this way, all right? Well, as we kept saying, the probability of doubles is 1/6, right? The probability of a 3 on green, that's a 1 die problem, right? That's just 1 out of 6. That's a 1 die problem. Now, the probability of both happening, right? By independence, right? Both means the probability of doubles and a 3 on green, all right? That's 1/6 times 1/6 by independence. 1/6 plus 1/6 minus 1/36. Common denominator, 6/36. If you don't understand what I'm doing, don't worry about it. 6/36 plus 6/36 minus 1/36 is 11/36. Okay, so if you're very formula oriented, you might prefer it that way. If you have no idea what I'm doing, I don't blame you. That's a weirder way of doing it, but you could do it from a formula, right? Probability of doubles is 1/6 or 6/36. probability of a 3 on green is 1/6 or 6 over 36. The probability of both, okay, well, oh, is it independence though? Yeah, it is independent, right? Because if I tell you I have doubles, then that tells you, then that doesn't give you any more information if it's 3 or not. All right. But in any case, what does P of both mean? P of both means specifically 3, 3, right? What's the only way you get both doubles and a 3 on green? Is if you get a 3 on green and also a 3 on red, right? So that's the probability of both. And the 3, 3 slot, that's 1 over 36. That's the guy I'm in danger of double counting. Because if you do 6 over 36 on the main diagonal here, plus 6 over 36 on the column here, you're in danger of double counting. In fact, you are double counting the circled guy, right? So you gotta subtract off the double counting. Subtract 1 over 36. That 3, 3 case is the intersection. Okay, if you didn't get that, don't worry about it. But that's a way of showing work. If you don't want to show the grid, here's the formula method of showing the work. Wow. Lesson 12, number 3. That's a ABCD, great probability problem. If you understood, well, especially if you understood this, then you understand a lot about probability. Any questions? You might want to think about this, right? Why does this work? Yeah. Okay, a question? Double counting is going to be the death of me. Yeah, I know. We got to watch out for it, right? Okay. You don't count the intersection. So, because if you don't do that, you're in danger of getting probabilities greater than 1. Actually, these problems are even harder because if you mess it up, your probabilities usually aren't greater than 1, so you can't even check it, right? At least if you get a tentative answer greater than 1, you know it's wrong. Here, you're not sure if you get the answer right or not. By the way, did I get the questions right? I would be shocked if I made a mistake, by the way. Okay, did I get my own questions right? Good question. I get my own questions right. I would be shocked if I made a mistake. Okay, so 3A was either 6 over 36 or 1/6. That's correct. B was 12 over 36 or 1/3. Remember, you don't have to simplify. C was 16 over 36 or 4/9. I remember that. D was 11 over 36. Very good, Ken. You can answer your own questions. Yeah. Well, counting is tricky sometimes, right? All right. Good probability question. Okay. Any questions or follow-ups on that? Feel free to review the video. And if you'd like me to come back to this, now for the benefit of the other students, I might want to do the problems here we're doing today at the end of Monday, because some people may have already gotten these. But if you ever want to go back and discuss these again, I'm fair game to discuss these up to an hour after class. So, but again, they'll have lower priority compared to the ones we haven't covered yet. All right. Who's next, by the way? Lesson. Okay, so here you are. Okay, so we've done check marks. We've done this, done that, that. Okay. If not to your satisfaction, then talk to me on Monday. All right. Requester, or maybe someone. Lesson 13, number 5. Requester, ideally, your favorite color, if you wish. Or you can throw it to green. All right, let's go to green. Good time for green. All right. What is this? 13.5? All right. And it's good for me to mark the guys here the same way. Yes. Okay. 13.5. This is on independence, dependence, and multiplying. Yes, exactly. All right. All right. Good applied problem, polling, and all that. All right. Okay. New whiteboard. I love my free whiteboards. By the way, I get this from taking a big text file and doing a screenshot. Get my free whiteboards. All right. All right. I'm having fun teaching online. I like my free whiteboards. All right. It's a lesson. What was lesson 13, right? Okay. Lesson 13, number 5. Let's do 5A first, obviously. Okay. Let's read this. In the recent presidential election in Fredonia, I didn't want to ruffle feathers by talking about the United States. So in the recent presidential election in Fredonia from the Marx Brothers, The Orange Party candidate received 55.7% of the vote. Now, remember, we want to convert that to decimal. What's 55.7% as a decimal? Pure decimal. Take this, 2 places to the left, drop that. You're dividing by 100%, right? You're dividing by 1, you're dividing by 100%. 0.557. And the 0 here is optional. I don't care if you put the 0 there or not. Okay, so that's that as a decimal, because remember, we tend to not like to compute things with percent. We like to convert to fraction or decimal. Okay, decimal is ideal here. All right. Okay, the Fredonia News Network, FNN. I know Fox is also FNN, but the Fredonia News Network presents a focus group of 10 voters in Fredonia who voted in that election, and they're claiming it's a random sample. The 10 voters represented less than 5% of the total number of votes in that election. Now, the reason why I mentioned that is that I'm telling you that the sampling rule is applying. So let me explain this. It's not a big deal for the problem, but conceptually it is. So why am I mentioning this? I'm saying that the sampling rule applies because we're sampling a tiny proportion of a large population. Okay, so because of this fact I told you, the sampling rule applies, which means that for all practical purposes, when we do our computations, we can assume what I word. Among the 10 voters, we're going to ask them who they voted for. We can assume what I property, which really gave us easy calculations.
Independence.
Think coin, good. Think coins, independence. Now, again, someone paying close attention might say, well, wait a minute. If you pick an orange voter first, aren't you a little bit less likely that the next person is orange? Like the cards, right? You're sampling without replacement. Well, yeah, you're technically right. But the thing is, because we're sampling such a tiny sample of a large population, for all practical purposes, the chance of picking the same person twice is so minute, we don't worry about it. We assume independence. Assume that you have a situation in Vegas where you have 1,000 decks of cards all shuffled together, right, in this massive deck. You may as well assume independence, right? Between the cards. Right, anyway, we assume independence for practical purposes. That's very important, right? Because we don't want denominators of 50 million or something, right? This will be a lot easier. All right. Independence helps us with calculations. Okay, so where's my... Here we go. A, what is the probability that 10 randomly selected voters, right? So we're kind of comparing what FNN got with our model here, right? What's the probability that 10 randomly selected voters who voted that election all voted for the Orange Party candidate, okay? Assuming an unbiased random sample. So basically, under the normal assumptions, the probability that all 10 voters were orange, that is, they voted for the Orange Party candidate. Okay. Again, we may assume the sampling rule and assume independence. Okay. All right. Now, you don't have to write it this way, but here's the idea. Let's talk about the idea first. Okay. Now, I don't care if you put them in alphabetical order or whatever, or random order. Voter number 1, okay? I don't care how you pick voter number 1 among the 10. Voter number 1, maybe alphabetically, John Adams. What's the probability that John Adams voted orange? Give me a number. What's the probability that John Adams voted orange? Random Fredonian in the sample. Well, 0.557. All right. By independence, what about voter number 2? Jane Baxter. What's the probability that voter number 2 voted orange?
0.557.
The same, right? 0.557.
To the 10th.
Exactly, right. Now, again, the idea is that, remember, technically there's dependence because if we picked an orange voter first, we're a bit less likely to pick an orange voter next, like the whole cards thing. But again, we're picking 10 people out of a huge population. The probability that we're going to pick John Adams twice anyway is minute anyway, so we don't care. All right, and you're right, exactly. You're going to have 10 of these copies, multiply together. Okay, here's your work. Please show a little bit of work. 0.557 to the 10th. That's your work. And the final answer is, I'm going to cheat. And you can, and if you're curious how many decimal places, it's okay to cheat and look at the answer. That's okay. Wait, where are my answers? Did I close that? I'm gonna have to reopen that sheet. Okay, hold on. There we go. All right. What was this? This was 13.5. All right. Yeah, here we go. All right. So that's all the work you need to show, but show it. Don't just give me the answer, all right? Because I want to show this bit of work, but if you want your points, you got to show me that bit of work, all right? 0.557 all to the 10th, and that turns out to be about that thing. And again, I wrote out to 3 sig figs. If you don't know how to round, oh wait, did I put the instructions? Or maybe not. Oh yeah. Write your answer as a decimal, round off to 3 significant figures. I did tell you how to round. I normally do. Okay, but that's that. So you don't have to cheat. You can. All right. So it is about the 0 is optional. 0 point, but you need 0.00287. Okay. If you wish, you could convert to percent. Okay, so that's the answer. That's the probability. Okay, but show this work. Any questions about that? All right. Describe that probability to me. The probability that all 10 random, right? There's supposed to be random voters. The probability that all 10 random adult Fredonian voters were orange, it's that. Describe that probability for me. 0.00287. That's pretty low, isn't it? That's really close to 0. Hence, part B, the practical inference problem. Part B, what do you think about the network's claim that the voters were randomly selected? Well, what do you think? The probability of this happening by chance is 0.00287. The Fredonia News Network says, hey, look at these 10 voters. And it turns out that all 10 voted orange. What are you thinking?
Sampling error or bias?
A bias. Yeah, bias. I don't think it's sampling error. I think it's bias, right? Yeah. What were my... Yeah, so the way I phrase in my answers, again, you don't have to phrase it exactly the way I did, but I said, and again, you can write this a bit differently. We would be skeptical of the network's claim. And the claim was that they were randomly sampled, right? The network claims that the 10 voters were randomly selected. And by the way, later on in the last part of the class, when we do hypothesis testing, we're going to formally test this claim in a hypothesis test. That's like the null hypothesis. All right. We would be skeptical of the network's claim of random selection because why? The probability of all 10 voters being orange voters by chance, assuming no bias, is way too low. Because again, 10 people on the stage, they're all voters, blah, 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 right? The probability that all 10 voted orange is that. So if the network's trotting out these 10 voters and it turns out all 10 of them are orange supporters, you as a viewer might be going, wait a minute. The chance of that happening just by pure chance and random selection, unbiased, is way too low, which means that I think that the network's fixing things. This network is in the pocket of the orange party. All right. Okay, questions. Again, you can phrase B in different ways. In these interpretation questions, I might be a bit more liberal. Okay, so you don't have to think. You don't have to think or write exactly the way I do, but that's the basic idea. Okay. Yeah. Once again, don't forget to check in. All right, and I do expect to email the homework 1 grades Sunday. I'm going to set a time limit for myself, but the pre-calc homework kicked my butt. Those of you who took me for pre-calc, you remember that how hard that homework assignment was. The monsters. All right. All right. Let's go back to the main list because we're approaching 9:30. All right. So we've done that. Lesson 17, number 6. All right, lesson 17, number 6. Oh, oh yeah. This is the one where it's short answers, but it's hard to figure out what's what. Yeah, I get that. Okay. But again, show a tiny bit of work. Show me what you're doing. All right. So, oh, pick a color. Pick a color. Requester, pick a color, if you wish. Okay. Color, anyone? Red. Okay, let's do it. Red. 17.6, red. Okay. Okay. Okay, so this is 17.6. 17.6. All right. All right. There are 10 questions on a math test. Okay, and if it helps you, you might even want to kind of imagine listing them out. You don't have to, but you can imagine listing them out. What? Zoom bar, go away. What's this thing? 2, 3, 10. All right. All right. Okay. You answer all of them. No partial credit is given. Okay. And in fact, I'm not saying it's even true, false, or multiple choice. They could be. Well, each answer is either correct or incorrect. Okay, so it could be free response. No, they're not like essays, but they can be like free response in a chemistry class. No partial credit is given. Each answer is either correct or incorrect. Okay, how many ways are there for you to get 4 questions correct on the exam? Ah, okay. So here's my question to you. Is it going to be 10 C4, like 10 choose 4, same thing? Or is it going to be 10 P4? That's really the question. That's really the question. Now, here's the key observation. Assume that the order in which you answer the questions does not matter, okay? So you just care about which 4 of the questions you got correct. How many ways are there for you to get 4 questions correct on the exam? So if I told you that you got 4 questions correct on the exam, how many ways were there to get 4 questions right where you didn't care about the order? Okay, so for example, if you got the first 4 correct, I don't care if you list them like this or like this. I don't care about the order. Which is it, C or P? It is, you're correct, C. 10 C4 or 10 choose 4. Okay, and I hope that you can use that button on your calculator, but the long way of doing it, remember, it's 10 factorial. Okay, because that's the total, or the number of total orders or permutations, but you don't care about the order of the correct questions, so you divide by 4 factorial, and you don't care about the order of the wrong questions, so that you also divide by 6 factorial. Hopefully you can get this on your calculator, and then you'll get, what is it, 252? What is that number? Not that I expect myself to memorize these, but 210. Yeah, 10-4, 10-4. Yeah, 210. Okay, so as far as work goes, I want you to show me that 210 ways. I don't care, 210 ways. Okay. On your final answer, I want you to show the 210, and I want you to show me at least one of these. All right. Show me at least one of these. 10 C4, 10 choose 4 means the same thing. The formula is fine. Give me 210 and give me at least one of these expressions. But don't just give me 210. Okay, give me something. At least one of these 3 on top of that. Okay. So here's the thing. In terms of, there's not much to write down, but give me the final answer and tell me tell me the basic expression. Like, is it 10 C4, 10 P4? Is it 10 factorial? Is it 10 to the 4th? Is it 8 times 3 times 13? Okay, show me the basic expression that got you to the number, right? So there's not much writing, but it's hard to figure out. Yeah, I know. If you pause the video, you can get it, but yeah, go ahead.
The basic expression meaning 10 C4, that?
Yeah, in fact, I'll take, okay, for the work, on top of the 210, the answer, I'll take any of these 3. 10 C4, right? 10, the number of combinations of 10 distinct items taken 4 at a time. So 10 C4 is fine. 10 choose 4 means the exact same thing. That's also fine. The formula, of course, is also fine. But I'll take any of these in addition to the answer, 210. But give me some rationale. I don't just want to see 210, because then I'll be like, well, you wrote down 210. Where'd you get that? What is that? All right. Now it's 9:35, but let me go ahead and answer the last one. Okay, 11:4.
Professor,
Go ahead.
I asked about 11.4 and I actually went back and I understood it. So, I mean, if anyone else needs it, sure, but I don't need it anymore.
Oh, yeah,
That was-
it's a long one, so we so how am I gonna do this? I'll probably do this on Monday.
Yeah, the only one that I was confused about was H, but really
Yeah.
it was
That's 5/36, right? Do you want to go over that?
H, yeah.
Yeah. What color, if you wish?
Green.
Green, sure. 4H, yeah. In fact, I may have discussed this in an office hour, but let's do it again. It's a fun one. They're all fun. I love probability. All right. Oh, I did this thing. I don't like doing that. Yeah. All right. 4H. That's lesson 11. All right. By the way, it's 9:37, but you know, trucking on. Lesson 11, 4H. Okay. Although what I might do from now on, since it's basically the end of class, after 4H, what I might do is I might address individual student questions and offer maybe some key hints or perspectives, but then I'll answer them on Monday, because we're at the point where some students are leaving, right? And they may or may not watch the video. So I might do some quick hints or responses after the 4H. Okay, so right here. What's the probability that the number on the green die is one more than the number on the red die? Ah, little math here. Yeah. Probably that was all math. Probably that the number on the green die is one more than the number on the red die. A little bit of word problems here, right? All right. So the probability that green is one more than red. Although if you had mixed these up, you get the same number anyway, right? Okay, so I'm gonna go back to my to a ye old grid, right? Look at the marginals again. All right, ye old grid, ye old grid. All right. Okay.
Do you want us to draw a grid for this question as well?
Yeah, either draw a grid or state for me the ordered pairs. Right.
Okay.
Okay. 1, 2, 3, 4, 5, 6. So you have to explain your answer somehow, convincingly. Green? It's the same as the base color, but 1, 2, 3, 4, 5, 6. All right. All right. Green. Okay, so give me some ordered pairs, folks. Red, technically it's red comma green, but give me some ordered pairs where green is one more than red. Okay, red, but the ordered pairs go red comma green.
1, 2,
Correct. 1, 2,
2, 3,
2, 3,
3, 4,
4,
4, 5,
4, 5,
5, 6.
and 5, 6. So again, you can either show me this grid with the check marks or whatever, happy faces, or actually write out 1, 2, and so forth. Write down the 5 ordered pairs. Okay, but convince me, right? Okay, so and then I'll believe you if you say it's gonna be 5/36, and that is simplified. Right. So avoid answer only. Basically, you want to write out enough work so that you can convince a colleague who needs to be shown things step by step. If you just show your colleague 5/36, and your colleague has to be shown things step by step, then your peer will go, "What? How'd you get the 5?" What the right. Okay. So and I know there's another one. There's an earlier request. Was it 14.4 or? I saw 14.4. Was that the one I was looking at? 14.4. Yeah, I saw. Okay, so I might offer some hints here and then elaborate on Monday, but I saw 14.4 in the list. And I also saw 16.3. Yeah. Okay. Now I'm still recording. Let me know if you want me to pause, but I'm still recording. But I think we're losing some people. I don't know, but we may have lost some people. So I'll give some hints, and then maybe we'll elaborate next time, or I'll just go over them next time. Okay. Okay. Well, just two more. Were there any others besides 14.4 and 16.3? And I realized that 11.4 had all those others, and we might want to take some time on Monday. In fact, I think a good deal of Monday maybe spent on 11.4, but 13.3, okay. Okay, and then maybe I'll skim these quickly on Monday. Yeah. Anything else? Okay. So I might go back and forth on those. All right. So 14.4. All right. Okay. Pick a color if you wish. See, 14.4. And we're going to focus on this table here. Color, any choice of color? Otherwise, we haven't seen purple yet. Want to go purple? Okay. All right. And in fact, I think I'll just write on here. I think we're okay here. I'll just write on the homework sheet. Okay. So Fredonia has 10,000 adults, right? That's this grand total here. And we have this two-way frequency or contingency table. What is the conditional probability? Okay, so what is the conditional probability that a randomly selected Fredonian adult, here are all 10,000 of them, that the adult owns a cat, given that the adult owns a dog? So it's important to get this order right. The probability of cat owner given dog owner, all right? Now, let's see. So if you wanted to look at it from a formula perspective, you could do it this way. It's the probability of both cat owner and dog owner, right? Dog and cat, over the probability of, it's the condition, okay? It's the condition. We're restricting ourselves to this world, the world of dog owners. And actually, instead of probabilities, I'm going to do the raw counts because each Fredonian counts equally, right? We don't have any twins or anything like that. Okay. I mean, we could, but we don't have to work in terms of probabilities. We can work in terms of raw numbers because each Fredonian adult counts equally. That's my point. Each Fredonian adult counts equally. We can deal with raw counts. All right. So we only care about the world of dog owners. All right. That's owns a dog. Yes, that's this column. Okay. And I don't care at all about the non-dog owners or these totals. Okay. No offense, but we only care about the dog owners. All right. So our entire world now is reduced to this column. How many total dog owners do we have down there? We have 3,000. Of those, how many also own a cat? 1,000. I'll accept this. This obviously reduces down to 1/3. All right. So of the 3,000 dog owners, 1/3 of them, 1,000 of the 3,000 also own a cat. And it helps to put a note like this. Could this be answer only? Possibly, but I think it's nice to put notes like these just for your benefit. All right. Okay, and in 5, I asked you for the probability of dog given cat, and that's going to be a different probability, right? Questions? Very quickly, before I go on, if you think in terms of a Venn diagram, right? Here's all adult Fredonians. Whoop. Here's all adult Fredonians. Okay, so here are the, let's see. Here are the cat owners. Here are the dog owners. All right. We only care about the world of dog owners. And of these, 1/3 of these are furthermore cat owners. So that overlap, red purple, is 1/3 of the red filled in thing over here. Yeah. Okay.
Professor,
Yeah, go ahead. Oh, okay, go ahead.
for number 4, so you put number of both over number of dog.
That would be
But-
nice. I mean, but if you were to ask me, would I give full credit for answer only? That's possible, but I think it would be nice for you to put some sort of note there.
No, yes, that's not what I'm asking though. What I'm asking is I don't understand the correlation between that and the actual numbers, because wouldn't both be 3,000?
Oh no, see over here. Okay, owns a dog. In the yes column, the 3,000 total here means the total number of adult Fredonians who own a dog. They would answer, if you ask them, do you own a dog? They say yes. There are 3,000 dog owners, right? That goes in the bottom. Okay. And you only care about them because on the top, see, the thing is on the top, I should have written this really. It's the number of people who own both a dog and a cat. That and word, that intersection. The number who own both a dog and a cat. See, these 1,000 people, they're the only 1,000 people for Donia who would answer yes to both questions. Do you own a dog? Yes, that's why they're in this column. Do you own a cat? Again, yes, that's why they're in this upper left cell. We have 1,000 who own both. All right. So basically, given that you own a dog, what's the conditional probability you own both? That is, that you also own a cat.
So number 5 would be then 1,000 over 3,500.
Correct. And you see it's different.
Yes.
Right? It's different. And they are supposed to be different. And in fact, we're answering 6 also. Do these have to be close? Well, actually, those are pretty close, but they don't have to be. They can be wildly different. Let's say that we have like 7,000 cat owners, right? Or do you remember the cooties problem, the medical diagnosis, the probability that you test positive given that you have cooties versus that you have cooties given that you test positive? They can be very different. For one, it was 80%. For the other, it was 7.5%. So these they could be close, but they don't have to be. They can be very different. And they certainly don't have to be equal. They could be, but they don't have to be equal, for sure.
Can you say that only the numerator has to stay the same?
Right, because in both cases, see what? Let's go ahead and do 5, right? What's the probability of dog owner given cat owner?
1,000 over 3,500.
Correct. So the numerator is the same because it's that upper left cell, but this time we want this. Do it in red. This time we want this row, and we want the 3,500 over here on the bottom. We want that. So that's why these probabilities can be different, because even though we have the same numerators, the denominators could be different. In fact, they could be very different. So in 4, it was 1,000 over 3,000. In 5, it's 1,000 over 3,500. Actually, they are kind of close, but they didn't have to be, right? What if this were like 7,000? Questions or follow-ups? Questions or follow-ups? So no, it's good that we're discussing, because otherwise on Monday I might have kind of just breezed through this, right? It's like, oh, it's this over that, and that's it. All right. Any questions? See, today we can actually talk about problems, right? Why they work, why the work works. Okay. So we've kind of done that. Yeah. Okay. 16.3. Yes. I can fill it in right here. Okay, requester, pick a color if you wish. Yep. Okay. 16.3. Color? How about maroon? All right, maroon. Rarely use that one. Okay. Give myself some credit before it's due. All right. Okay, so bottom line, and I know I got this. I tried to get the semantics right, but bottom line, your family pays $1,000 for the life insurance. If you die, your family will get a $100,000 check from the company. All right. So ignoring the value of your own life, right? I mean, right? Okay. Of course, your family will miss you, right? Let X equal you and your family's net monetary gain as a result of the decision to purchase the policy. All right. So we're not looking at the value of your life as a human being. We're looking at the money, pure money. All right. Okay. So what are the values here? All right. You live. Well, if you live, your family doesn't get anything. Okay. So they don't get a check from the company, but you folks still had to pay the $1,000 premium, right? Oh, I don't need this. I don't need that unit here, right? But 0 minus 1,000, all right, that's going to be negative $1,000. Okay, so that's the value of the insurance policy if it turns out you live, the monetary. It's a net loss of $1,000 for your family. Okay, now what's the value of the policy if you die? All right, well, your family gets a check for $100,000. You should probably type this. Okay, a check for $100,000. But, okay, you don't get your premium back. That's still out there, right? So then that's going to be a net gain monetarily of $99,000. Okay, now once I put in the probabilities, we're going to have a probability distribution. I realize that you're not getting nice integers like 0, 1, and 2, but once I put in these probabilities, you're going to have a probability distribution. I tell you, based on your health or whatever, right, the probability of you dying during the year is 0.004. That's over here, 0.004. That's the probability you die actuarially based on who you are, right? Like whatever, you're a 35-year-old male, whatever. Okay, which means, hey, now we're saying that you either live or you die. Let's not say that comatose is a neutral thing. You either live or you die after the year, right? How do I figure out the complement? What do I do? How do I figure out the complement?
Take that away from 1.
Correct. Okay, 1 minus 0.004. Again, it's nice if you show that, but I doubt I'd require that. But okay, over here, 0.996. Now I do want to see this. Oh, absolutely. You have to fill out the table. Yeah, I tell you, you absolutely have to fill out the table. Okay, and it better match up with mine. This is 16.3, right? Yeah, here we go. All right, and it matches up with mine. Negative $1,000, $99,000, 0.996, 0.004. The zeros to the left of the decimal point are optional. All right. All right, folks. You agree with the table then, right? You agree with the table. Questions? Questions? Okay, because that's part of the problem. You got to put this in. And then, as far as, I mean, if you wanted to like copy paste the table into your homework, that's fine, whatever, right? Okay, now how do you do E of X? Expected value. That is the zigzag. What do I mean by that? Different ways of doing it, but basically it's whatever. This times this plus this times this, right? Zigzag. Again, different orders you can do it in. I'm going to ignore the unit for now. It's negative 1,000 times 0.996 plus 99,000 times 0.004. Okay. By the way, one shortcut, although the table didn't suggest this, was that you could have had $0 and $100,000, work it out, and then subtract the $1,000 at the end. But I want to be able to do this to demonstrate the zigzag. All right. Okay, and I trust, now write this out. Do show this work. I want you to show this work. Show me the result of your zigzag. That's work, okay? And then work that out, and then you better get, what do you get? Work that out. What do you get? And you better get dollars. It's expected value of X. X is the net monetary gain for your family monetarily. It's the expected value of X. It's the mean of this probability distribution. And this is going to be, it's equals, I guess. It's going to be negative, isn't it? Because insurance companies are out to make money, right? So this better be negative. Otherwise, the insurance company is going to go out of business. Negative what? Negative, what is it? Negative $600, right? Exactly. Negative $600. And what does this mean? And this is where, my little handout's helpful. Any questions about the calculation? Well, that's nice. The mean of this distribution is negative $600. What does that mean? All right. So here's what I say. Again, you can word this a bit differently. Okay. But if you word it verbatim, I don't blame you if you want to be safe. Over many customers in a similar situation as you, right? So the same health probabilities and all that, right? Over many customers in a similar situation as you, the long run average net loss for each family is about $600 per family. Okay. So imagine a bunch of people who are like you actuarially in terms of health, gender, whatever, right? Okay. Then if you consider all those people and if they all buy this $1,000 policy, then on average, it's going to be about a $600 loss per family monetarily. Of course, because the insurance company is basically making $600 per family. Insurance companies are out there to make money, right? Oh my. There's a movie called Two Strangers on a Train. It's about two strangers who meet on a train. It's a Hitchcock movie. They each hate someone. Like someone hates his. I think they hate each other. I think they hate their wives. And then they try to set it up so that they kill each other's wives. And the idea is that since people don't think they're connected, there's no motive. So that's a Hitchcock film. Two Strangers on a Train. These two guys who try to get away with it. I forgot the ending. I forgot how it ended. But so these two guys, they're like random people who met, but then it turns out that they wanted to kill their wives, and they arrange it so they kill each other's wives, and that's how they try to get the insurance money or something like that. Yeah, there have been any number of detective stories that have done this thing. No, it's not legal. You're joking. All right. All right. Any questions? The thing is, I'm very precise. When I read things, I take things literally. I'm one of those people. So it's like, yes, I'll answer the question. What if you kill someone? Hypothetically. All right.
Professor,
Yeah, go ahead.
for question 13.3.
3. Is it
13.3.
Yeah, 13.3. Let me
Would the answer be the same as 2? Is it like a trick question, or is this
No, they're
because-
different. No, because 2, that's when you're drawing with replacement. That's when, as soon as you take a card out, you put it back in the deck. So you have independence.
Okay, so would number 3 have 3 separate answers or just one?
Well, the thing about 3, here's the way to think about 3. It's a different process. When you take out a card, you leave it out. Here's the first card, it's left out. Then you take another card out.
So would it be 13 over 49?
Well, now these are probability problems, right? So your work here is going to involve showing me, like here it's going to be 3 different fractions and multiplying them together.
Okay. Oh, okay. And each one, the denominator decreases by 1.
I'll start you off. Okay, so here's one that I'll start you off on. So what's the probability that 3 cards are all hearts? Okay, now remember there are 13 hearts out of 52 cards, right?
Mm-hmm.
I know it reduces to 1/4, but it's actually easier if you start with. So what's the probability? What's the probability the first card is a heart? It's 13 over 52. You agree, right?
Yes.
Okay, that is 1/4, but I'm going to try to make a point here. Okay. Times the probability that, okay, times the probability that, assuming that the first card is a heart, what's the probability the second card is a heart, given that the first card is a heart? So the conditionals matter. It's not going to be the same. You raised a good issue. Okay, once you take out this card, how many cards are left in the deck?
51.
Not 52, 51, right. And assuming that the first card is a heart, how many hearts are left?
12.
Assuming the first card's a heart and it got taken out, okay, how many hearts are left that are possible for the second draw?
12.
12, correct.
So you would write 12?
Yes, 12 over 51. And then hint, there's a third fraction, and you multiply these together.
So, okay, so it'd be 11 over 50.
You're right. And then you'd multiply. You're right. Show that work. You absolutely have to show that work. Okay. You don't have to write the P of blah, blah, blah. That might take forever. If it helps you, great. But I need to see this. If you want to write the P of, A times P of B given A, all that stuff, that's fine. But I want to see this.
What is the result of this?
Oh, what's the answer?
Yeah.
Yeah. Was this 13,
Is it-
13.3?
Is it 0.0129?
I have no idea. I know it's low, but 13.3.
Yeah, it is 0.0129.
Okay, great.
Yeah. And I asked
Thank you.
I asked you for write your answer as an exact, or write your answer as an exact. Oh, wait. Write your answer as an exact fraction and also round it as a decimal to 3 significant figures. So I want you to write down either of these two fractions and also the decimal approximation.
The first 0 does not count as a significant figure, correct?
Correct. The 0 here does not count to the left of the decimal point. In fact, the 0 to the right doesn't count either. Remember, significant figures or digits, you start counting at the leftmost non-zero digit. So I could have like a billion zeros out here. If the first non-zero entry is a 1, that's where I start counting sig figs. So this is written out to 3 sig figs. 0.0129. It's to 4 decimal places, but it's to 3 sig figs. Okay, that issue comes up in higher math and chemistry and physics. Right? And again, I want you to show this work. You don't have to show me this stuff over here, right? If it helps, great. But you got to show me as work these 3 fractions. You got to show me that work. Show me the countdowns. Okay, you must show this. And then either this or this and the decimal. This is optional. If it helps you, great. But
What is that fraction at the bottom? 1,760.
oh, that's okay. That's if how do you multiply fractions? You multiply the tops, right? And you get 1,716. You multiply the bottoms and you get 132,600. And I'd accept this fraction as your fraction. It happens to reduce to that, but why bother with that, right? I mean, it's okay if you write it like that. See, part of the reason why I wanted people to do that was that it encouraged people to show the work. Okay, I really wanted people to show the work, and that's a way of encouraging people to do that. I wanted the people to think in terms of fractions first. Yes, I know it's partly an exercise of how much work do you show, but that's why you come to class, and you right because I'm training you to be good stats tutors, and we need more of those. Show your work. Show your work. I have the right to grade on work, as I specify in class and lecture and the notes. Some are answer only. If I ask you, what's the probability of a heart on one card? 13 over 52. Box it in. Go on. Okay, I know some are answer only, but if you can't show work, show work. The 33, that was the one that we answered, right? Okay. All right, so it's an open form. It's 10:03. I appreciate your conscientiousness, and we'll do it again Monday. Although some of you, hey, if I answered all your sticking points and you feel confident about the answers, you might still want to come Monday to check with me, right? Yeah, I wouldn't recommend turning in your homework before Monday because you want to see the answers. But then you can turn in very quickly, like 10 minutes after class or something. Just get rid of it. You don't have to rush, but okay. Was there anything else? That's so funny. You had to say, yes, I'm joking. Yeah, of course you're joking. I see a question in chat and I just have to answer it anyway. Oh, okay. So just zone out for a moment. Okay, so any Any more questions that I can explain, or would you be ready for the skim on Monday, where I just go boom, 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 and then well, then if there's work that you're concerned about, you can ask me after class, but you might not want to stick around afterwards on Monday too long, right? You want to try to get things done now, get things pretty good. And then Monday's like the final sheen, right? Making sure you got all the numbers right and appropriate work. Actually, the good question there was, would the family get the money if there's some sort of foul play? But still, I don't think that's the case. Now, I remember seeing movies where the plot twist would be that it was all about the insurance money to help somebody else, like your family. In private chat, not for the public. Do you know what movie I'm talking about? A movie where there's a murder and it's because the guy wanted to help his own family. There's a particular movie I'm thinking of in private chat. Do you know what movie I'm talking about? It came out around 2004 or so. There might have been other movies. I'm sure there are. If you're curious what movie I'm talking about, private chat me. A movie where the guy tries to commit a murder and it's for his family. Oh no, no, no. It's not the murder. No. He's trying to convince people that he was murdered. He's trying to convince people that he was murdered by this other guy. He was murdered by this other guy. And then his family would get money because they want to set up the guy. They want to set up the accused murderer. Do you want me to give it to you? Private chat me if you want me to give it to you. Okay. Or any stats questions. Any real stats questions.
Hey, can I ask something quick?
Go ahead. Huh?
So where can I see this video?
Okay, so
On the YouTube?
Yeah. So what's going to happen is I am recording this, so it's going to save on my computer, and then it might take like an hour or so for it to process. But once it processes, I upload it on my YouTube. So if you go to my website, I have my playlists up, right? And then I add this to my playlist. So all my class videos I add to the regular playlist of videos.
You mean the YouTube playlist?
Right, the YouTube playlist.
Okay, all right, thank you.
Right. So on today's day 13, right? So I have the one on my funky midterm. That was the only video for day 13 I have right now.
17th.
Right, March 17. Yeah. So I just have right now the video on my midterm, but then I'm going to add this video tonight, and then I'm going to add that to that playlist, and that's going to be by midnight or so.
Okay, all right, thank you.
You're welcome. All right. Is there anything else, or would you like me to hang on? Are you kind of flipping through things? Any questions? Okay. Yes. Good night. For some of you, I'm still awake. So, but if you're getting tired, I don't blame you. We've had a good night, and thank you for your conscientiousness. That includes you, the current audience, and you watching this video. Okay, I appreciate you watching this video. Okay.
What is the definition of conditional probability again?
Oh, okay. It's like an updated probability. All right. So
Oh,
yeah, so let me go back to I'm going to go back to my lecture notes. Okay. So yeah. Okay, I'll go back to this. Or I might be able to just get another. Okay, do you feel comfortable with a deck of cards? You know how a deck of cards works?
yes.
Okay, so here's a way of looking at it. Okay, so I'm going to repeat an example I did earlier that illustrated this. So let's say that you want to know, okay, so what's the probability that if you draw a random card out of the deck of 52, you get the 3 of hearts? In other words, 3 and hearts. Okay, so if you want to do like a grid like we did for the dice. Okay, so here's our all right. So 2, 3 up to ace, hearts, diamonds, clubs, and spades. All right. Okay, so the 3 of hearts. What's the probability we get the 3 of hearts? Well, that's only one card out of the 52, right? So that's 1 over 52. So you have a deck of cards. It's all shuffled. You randomly pick one. The probability it's this particular card, the 3 of hearts, that is, it's a 3 and it's hearts, is 1 over 52. You agree with that?
Yes.
Well, now, what if we consider this? The probability that it's the 3 of hearts, given that it's a 3. Okay, so now here's where we're looking at it.
So just hearts given a 3.
Right.
Basically.
So there's a deck of cards here. Okay, you randomly pick one. Okay, and I look at it. Okay, I look at it, and I tell you, hey, you got a 3. The card that you picked is a 3, which means that it could be any one of these 4 cards, right? 3 of hearts, 3 of diamonds, 3 of clubs, 3 of spades, right?
Mm-hmm.
Okay. So you know that you have one of these 4 cards, and I'm being honest. Now, given that you know it's a 3, what's the updated probability is the 3 of hearts? It's no longer 1 over 52. It's 1 over 4. So let's say that let's say you love the 3 of hearts. You're really hoping that your card is the 3 of hearts. If you just take a deck of cards, okay, and you randomly pick one, then the probability you get your favorite card is 1 out of 52, right? It's fairly low, okay? But let's say that you take out a card, I look at it, and I tell you, hey, your card is a 3. Then you get a lot more excited because your updated probability of your favorite card, the 3 of hearts, is now 1/4, right? Right.
So the denominator changes in conditional probabilities.
Typically, yes. Yeah. If you're thinking very mechanically, right.
Okay.
Okay. Or in other words, if you do a Venn diagram, okay, so here's the world of 3s. These are the cards that are 3s. Here is the 3 of hearts. If I tell you have a 3, that means that you're in here somewhere, which makes it more likely that you have the 3 of hearts. Whereas if I didn't tell you have a 3, then you have a big sample space here. It's really unlikely you got the 3 of hearts. But if I tell you got a 3, you have a shot. You have a 1 in 4 shot of getting the 3 of hearts.
So
by the way, normally there is overlap. They usually look more like this. Cats and dogs. It looks more like this. This is a case where it's a bit more precise.
So let's say they're asking for a probability of hearts given that the card is black. Would therefore the probability denominator be out of 26? Because
okay. Now the way you're phrasing it, let's talk about that. The probability that the card is hearts, given that the card is black. But no, wait a minute. What color is hearts? Is it red or black?
Oh, I'm so sorry. Spade.
No, that's fine. It's red. The probability is what? The probability is. So if you draw a card and you want a heart, but I tell you it's a black card,
well, that would be 0.
That'd be 0. Right. That would be your updated probability. Because if you like hearts, Okay, you take out a card, I look at the card, and I tell you the card you drew was black. Then you go, well, there's no way I got hearts then if the card was black. But that you're updating the probability because the probability of hearts alone is 1/4, right? But if I give you information, if I tell you, hey, the card's black, that's useful. There is dependence between these events. If I tell you that the card's black, there's dependence. That means that there's no way the card is hearts.
Mhm. So what if it's hearts given that it was red? Would it be 26?
That's the idea, right? The idea that okay, now how am I going to put this?
Because 52 divided by 2 is 26, and there's half red and half black, right? So the denominator would be 26.
Right. So here's a way that you can look at it. One way you can look at it is that there are 26 red cards. Of those, 13 are hearts, and
Yeah.
all hearts are red cards, right?
Yes.
So 13 over 26 are 1/2. That's one way of looking at it. And that's similar to this picture because in fact, I can split this right in half, right? So here are the red cards in the left block here, right? And half of those are hearts, right? Half of those are hearts versus diamonds. Okay. So overall, see, there's a 1 in 4 chance you have a heart overall, right? But if you know that you have a red card, then it's up to 1 in 2, right? So it's 1/2 because you either have a heart or a diamond, and these are equally likely. So the
Yeah.
information that you have a red card, you're twice as likely to have a heart than if you just drew some random card from just a raw deck because the black cards are in there too.
Hmm.
So here's clubs, and here's spades. Ordinarily, red is ordinarily hearts is 1 in 4. But if you can get it down to red card, it's now 1 in 2. So we're talking about the concept of conditional probability. The idea that the condition gives you additional information that may force you to update the probability. You're updating from 1 in 4 to 1 in 2. My approach is called Bayesian, the idea of updating probabilities. Some pure math people don't like the idea of updating, but in Bayesian statistics, which is commonly accepted, it's the idea of updating probabilities given new information. Okay. Any other questions? It's 10:18, but I can still stick around a bit. You want me to check in at 10? I'll check in at 10:20. So in 2 minutes, I'll check in, see if there's any more more questions or comments. 10:20, give a couple minutes. Good night. Yeah. I'll see some of you Monday. Okay. And clean up the homework so that when you see the answers Monday, you could turn it in right then if you wish. No rush. Turn in Tuesday. That's fine. There's no advantage in turning it Monday over Tuesday, but let's say you want to get rid of it. All right. I'll check back in a minute. Okay, it's 10:20. Are there any questions, or would you like me to hang on for another couple minutes? Okay, I'll go ahead and stop the recording.